Welcome to day 7 of AI Advent Calendar. We'll be talking about neural networks today. We'll journey through the exciting world of artificial intelligence, starting from basic perceptrons to advanced neural network architectures like CNN, RNN, and LSTMs. Let's start with a simple example. Imagine it's early in the morning. I step out onto my veranda and look outside. There is so much to take in: buildings, houses, colors, the sunrise, maybe even the birds flying by. But my brain doesn't process everything all at once. Instead, it focuses on what's important to me at that moment. First, I realize it's morning because I see the sun has risen. Then I notice it's bright sunny day. As I stand there, I hear a lot of sounds in the background: bird chirping, distant cars, maybe people talking, but there is one sound that catches my attention. My brain focuses on it and tells me it's someone speaking. It identifies the language English and it picks out the name Anjani. Finally, I understand it's someone greeting me good morning. Through all this, I'm still aware of rest of the world around me, but my brain prioritizes only what is necessary, filtering and activating the information that matters the most at that time. That is exactly how neural networks work. It's presented with a lot of data, but it selectively activates only the important part, processes them step by step, and interprets them based on the relevance. This is where the concept of activation functions come into play. It decides what gets attention and what doesn't, just like our brain do in every day. The neural networks are inspired by the human brain. They consist of layers of connected nodes or neurons which process data to identify pattern and make decisions. Think of it like mimicking how we recognize objects, sounds, or even learn new skills. They are structured into three main layers: an input layer, where the data enters, the hidden layer, where the computation happens, and the output layer, where the results are produced. At the core of the neural network is a perceptron, the simplest form of neural network. It takes multiple inputs, assigns weight to each, sums them up, and passes the result through an activation function to make a decision. The decision making process is like drawing a line to separate data into different categories: important, not important. Also, for example, a perceptron could help determine whether an image is a dog or a not, or a cat or a not. When we stack multiple perceptrons together, we get a deep neural network. Each layer learns to extract increasingly complex features from the data. The multi-layered structure allows network to tackle complex tasks like, for example, handwriting recognition or image classification. Let us now learn how the machines learn to see the world, or more about convolutional neural network. Going forward, we'll be referring to it as CNN. The first lesson for the machine is to identify basic details. The convolution layer scans the image in small patches, detecting simple patterns like edges, curves, or even textures. It's learning to spot the building blocks of what it sees. Next, we help the machine focus by removing noise and distraction. This step, handled by the Redu layer, ensures only the important part of the images are kept, just like clearing a foggy lens to see more clearly. Once the machine can see clearly, we teach it to simplify. The pooling layer helps it zoom out and summarize the image, keeping only the essential details like recognizing that it is this shape is a cat's ear or a tail. Once the machine can see clearly, we teach it to simplify. The pooling layer helps it zoom out and summarize the image, keeping only the essential details like recognizing that this shape is ear or tail. Finally, we teach the machine to put everything together. The fully connected layer combines all the learned features to make a prediction that this is a cat. At this point, the machine has learned to see and understand the image. By teaching the machine to see step by step, CNN can recognize objects, identify faces, and even interpret the world around us. It's a remarkable process that powers countless technologies we see every day. Now, imagine a computer that forgets everything it just learned the moment something new happens. That was the world of artificial intelligence before the recurrent neural networks, or RNN. Traditional programs were like tourists with amnesia. They could only focus on what was right in front of them, unable to connect past experiences with the present moments. RNN changed the game by giving AI a memory. They can hold on to information from earlier steps in a sequence, like a guide taking notes along the way. The ability allows them to make sense of sequence data, such as time series, speech, or text. Let's see how RNN works. Imagine reading a sentence like I love neural network. As each word is processed, the RNN remembers the context. I love implies an emotion, and neural hits at something related to AI. This memory helps predict or understand the next word. RNN are unique because they process data step by step, passing context forward through hidden states. The ability to remember and connect sequential data is why RNN is so effective in tasks like language translation, speech recognition, and stock prediction. But RNN have their limitations. Over time, they struggle to retain older information, a challenge known as the problem of long term dependencies. For instance, remembering the subject of a sentence at the beginning can become difficult as the sequence grows longer. Now imagine a computer trying to understand a long, complex story without help. It forgets the beginning by the time it gets to the end. Here's where long short term memory or LSTM comes in. The impossible memory machine. These powerful tools taught machines how to remember, organize, and prioritize information over time. The forget gate is like Marie Kondo for computers. It decides what information is no longer useful and clears it out. For example, if the subject of the conversation changes, the forget gate ensures outdated details don't clutter the memory. The next comes the input gate, which decides what new information to store. This ensures the machine focuses on the most valuable data, like remembering a character's name in a story or a key trend in the stock prices. Finally, the output gate determines what information to use at any given moment. It decides what's most relevant based on the current context, ensuring the machine stays focused on the task at hand. In short, LSTMs are ultimate memory machines. They give AI the ability to remember the past, focus on the present, and predict the future, making them an essential part of the modern machine learning. While LSTMs are powerful for handling long term dependencies, there is another simpler alternative called gated recurrent units or GRU. GRU streamlines the process with fewer gates, making them faster and easier to train, yet effective for many tasks where a lighter model is sufficient. In summary, neural network ranges from simple perceptron to advanced architectures like CNN and LSTM, each tailored to specific tasks. They power innovation in healthcare, finance, entertainment, and more. Thank you so much for your time today and see you again tomorrow.